My name is Conwoo, and today I'm going to introduce my work on mmWall, a reconfigurable metamaterial surface for millimeter wave networks. So I'll get started. Uh, Today, demand for 5G network surges as the bandwidth requirement of the wireless applications grow. For example, we have witnessed major advances in virtual reality and augmented reality and mixed reality in the entertainment industry to provide immersive game experiences, as well as in the educational institution to help, for example, in guiding curated objects in the museum or to enable lifelike training simulations. Another example of such application would be a smart home and smart retailer, where all the devices are equipped with the internet services and content with each other to stream its own data. Robotic automation also requires high-speed connectivity to stream video to a backend server to accomplish some collaborative tasks. However, today's wireless network simply cannot support high data rate required for such applications due to limited bandwidth. So mobile operators and service providers have recently turned their attention into new 5G technology, which uses millimeter wave frequency to give us a huge amount of bandwidth compared to the current 4G deployment. So how does the use of millimeter wave frequency provide us huge bandwidth? Based on communication principles, the higher the carrier frequency is, the greater the signal bandwidth. More specifically, while the common 4G LTE band at 2 gigahertz frequency, carrier frequency provides a spectrum of around 100 megahertz, the millimeter wave can easily increase its spectrum bandwidth by a factor of 5 to 10 times, enabling data rate of multiple gigabits per second, which is a massive increase in the transmission speed. And we also want to note that the currently 4G bands are already extremely crowded, so we must explore other bands, other spectrum to be used. However, the biggest challenge of millimeter wave technology comes from the blockage of the signal. This is because the electromagnetic waves have a weak ability to diffract around obstacles with a size significantly larger than its wavelength. Since millimeter wave has such a short wavelength, it first experiences a huge transmission loss whenever it penetrates the wall. Also, whenever the human body walks across the communication path, the link is likely to experience a SNR drop of 10 to 20 dB, resulting in a frequent communication glitches. So these two challenges of high loss and communication glitches render the indoor deployment of millimeter wave much more difficult than the 4G communication. So our approach is to design a smart surface that delegates or relays the task of the AP at the wall. So here we can see that the AP and the user are separated by the wall. And without the smart surface, the beam would likely to be attenuated and then get wider as it approaches towards the user. With our mmWall, we want to not only relay the beam, but also focus and steer to the direction of where the user is located. Also, to avoid the human blockage, our smart surface also enables the path diversity to provide an alternative strong path to the user. And besides the beam relay and steering, our smart surface is capable of creating multi-arm beams, and this multi-arm beam functionality can be leveraged in multiple applications. So first would be the beam search. So current solution for aligning narrow millimeter wave beam is to scan the entire space to find the best direction, which incurs a large time delay. By generating multi-arm beams with different spatial directions and sweeping them concurrently, our mmWall can enable a fast beam search at the wall. Also, the multi-arm beam functionality can be used for multicast by creating and directing one beam per each user. Here we have visualized only transmissive use cases, but theoretically our mmWall can provide the same functionality reflectively when the AP and the users are co-located in the same room. So there has been previous works on smart surfaces. So first work I want to address is the Laya, which helps the endpoint by collecting the radio energy from the one side of the wall and phase shift it and transmitting to the other side such that the signal combines constructively at the user side. Similarly, our focus switched the elements to simply turn off the signals that are deconstructively combining at the receiver. However, both devices operate at 2.4 gigahertz, hence their goal is intrinsically different from our case. Due to low frequency, they don't address the issue of beam directionality, and the effect of the blockage is negligible. Instead, our goal is to deal with the beam directionality and the blockage. On the other hand, MoVR is a smart reflector operating at millimeter wave frequency designed for wireless VR application where the AP and the users are located in the same room. And however, it cannot relay the beam in transmissive direction, nor it can create the multi-arm beams. Specifically, the most limiting factor of MoVR is in its full duplex design, meaning that it has to receive the beam from the AP, amplify it, and transmit the beam. And such design requires multiple RF chain and multiple RF amplifier to generate multiple beams, resulting in a huge power consumption and complex hardware design. So we want to design some smart surface that's fast and fully steers one or more narrow beam, whether it's reflective or transmissive direction, without using a full duplex design. Is this possible? So we're asking on our question that at millimeter wave, can we naturally refract or split the beam instead? To do so, we explore a concept of metamaterial, a material that is artificially engineered in the sub-wavelength scale to exhibit a unique electromagnetic property that does not exist in naturally occurring material. So we know by experience that every material has like gold and silver has consist of atoms, and similarly metamaterial is composed of meta atoms that is size less than wavelength over 10. For example, among different electromagnetic waves, millimeter wave has about 12.5 millimeter wavelength. Thus, the size of meta atom should be around 0.1 millimeter. And using this different types of metamaterial, recent work has proposed to alter existing signal in the environment itself, such as creating materials with negative refraction index, engineering complex beam patterns, and manipulating signal polarizations. Especially, we are more focusing on one type of a metamaterial, which is called as Huygens Metasurface. It has gained an attention as a new paradigm for beam refraction, beam forming, and perfect reflection due to its key features. The first feature is the full transmission phase coverage of 360 degrees, and second feature is a near unity transmission. Structurally, is comprised of a layer of co-located orthogonal magnetic and electric meta-atom facing each other across dielectric substrate. So magnetic meta-atom is in the front here, and it induces the magnetic response. And electric meta-atom is behind the magnetic meta-atom, and it induces the electric response. When the incident field passes the metasurface, it is converted to transmitted field through a field discontinuity sustained by the electric and magnetic response from the Huygens metasurface. In other words, by inducing a desired magnetic and electric response, we can provide an abrupt phase change to an incident wave. So let me dive in deeper on how each magnetic and electric meta-atom induce a such desired magnetic or electric response. So first, for magnetic response, it is a metallic ring that induces the magnetic response by acting as a resonant LC circuit. And what is LC circuit? It's a circuit with a capacitor inductor that is engineered to naturally oscillate at the resonant frequency due to resonant exchange of energy between inductive currents and the field inside a capacitive gap. And the resonant frequency is calculated by the inductance and capacitance of the ring. And as shown here, the capacitance induced by the gap which is determined by width of the ring and the gap length of the ring. And the inductance is determined by the area of the ring. So let's say there is a EM wave coming in. And this EM wave matches the resonant frequency designed by this LC circuit. And what happens is that the magnetic field of this EM wave, as it passes through the metallic ring, it induces the rotating current. And this rotating current in turn produces its own magnetic field, which interacts with the magnetic field of the EM wave. Similarly, for electric meta-atom, it induces electric response by acting as a resonant LC circuit. Here, the difference is that it has one more gap capacitor, other than the magnetic singular capacitor in magnetic meta-atom. So here, we can see that EM wave, the electric field of EM wave as it passes through metallic ring, it induces rotating current. But here now, the rotating current are in vertical direction. So as it passes, the ring produces its own electric field in vertically. and it interacts with the electric field of the incident wave, and thus changing the phase. However, we must note that this design shown here have a fixed inductance and capacitance value, thus providing only a single phase shift, as you see here. This means that the design is not reconfigurable. And to steer the beam in arbitrary direction, our meta surface or each meta atom need to be able to provide different range of different phases. So let me first explain why we need different phases for beam steering in the first place. To do so, we can revisit the mechanics of how the conventional phase array antenna works for beam steering. So as let's say this is the phase array antenna, and as the sinusoid wave that the antenna sends out travels, they constructively or deconstructively interfere with each other. So if we design our array correctly, they will all add together in a narrow beam in one specific direction. And here we send out a wave at the exactly same time, resulting in a narrow beam perpendicular to the antenna. Then how do we change the direction of the phase array antenna? What we do is we apply different phase to each antenna. So um, the direction in which they add together into narrow beam changes as we change the applied phase shift. And the direction basically depends on the phase shift. So similarly for Metasurface, we need to be able to provide arbitrarily phase shift, and in order to provide different phase shift for Metasurface, we need to somehow change the inductance and capacitance value of our meta atom. And to change the LC value, we load the tunable electric component varactor on each magnetic and electric meta atom. More specifically, varactor is known as a voltage-dependent capacitor. So to explain this, let me go step by step. So let's say we load the varactor on the magnetic meta atom, for example. Then we have a two capacitor, gap capacitor, and which is a fixed value, and we have a capacitor induced by varactor. And since two capacitors are connected in series, we can calculate the total capacitance as follow, and the resonant frequency would change accordingly. So let's assume that we initially apply 0 volts across the varactor. Then let's say we have a resonant frequency at 24.2 gigahertz. Then let's say we increase the voltage to 1 volt, then what happens is that this would decrease the capacitance of the varactor, which would in turn decrease the total capacitance and increase the resonant frequency so that it would shift the resonant frequency. So you can see that as we increase the voltage, we will shift the resonant frequency. And what happens is that let's say that we sweep different beams, and then there is a different voltages, and there's a beam with carrier frequency at 25.4 gigahertz that hits them at the surface. And if we take a cross section at that frequency, we can get different phase shifts, so that we can provide different phase shift by modulating the voltages. So here we only discussed a single case with a single magnetic meta atom. And now let's visualize what happens as we vary the voltage across varactor on both electric and magnetic meta atoms. So here we loaded the varactor on electric and magnetic side. Then what happens is that we get some transmission pattern over varying voltages on the electric side on the y-axis and magnetic side on the x-axis. And this is known as a Huygens pattern. And as you see, the left is the magnitude of transmission and right is the transmission phase. And on right specifically, we can observe the phase coverage of 360 degrees. And thus we are now able to say that our metasurface is reconfigurable and is able to apply different phases. So let's dive in deeper of how we steer the beam using mmWall. So let's say there's a meta-atom pair, and we apply 0 volt in magnetic side and 0 volt in electric side. And if you see in the Huygens pattern on the right, we have applied the voltages. So we visualize in this way. And let's say we have a adjacent meta-atom pair too, where we apply 1 volt for both side, electric side and magnetic side. Then here we get slightly different phase. Let's say it's 1 phi. And again, once we apply 2 volts by 2 volt, we get 2 phi, and so on. And like conventional phase array antenna, now that we can steer the beam into arbitrary direction. So let's say we want to steer it into larger angle or steeper angle, then what we do is we increase the gap of the applied voltages on magnetic side and electric side. Then we can steer it to a larger angle. And we also want to note that if you see the transmission, we are able to get high transmission magnitude, meaning that we have a high efficiency for the outgoing beam. And now we ask question, how can we generate multiple beams? To generate multiple beams, we introduce additional degree of freedom in the control line known as time. So previously we applied DC voltage. So over time, we applied the constant voltage across magnetic side and electric side. However, and also this results in constant transmission signal where if we do a Fourier transformation of this, we will get an impulse at the carrier frequency and thus able to steer a single beam. But if we modulate this over time, what happens is that the resulting transmission would also be time varying, that once we do a Fourier transformation of this, then we will get multiple beam at the desired location based on how we modulate the time varying voltages. And let's say the time varying voltage here provides the two beam at the carrier frequency minus omega and carrier frequency plus omega. Then what happens is that uh, using the obtained time varying voltages, we apply it into meta pair 1, phase shift it, and apply it to meta pair 2, and then phase shift it much further and then apply it to meta 3. Then what happens is that we can concurrently steer the beam, two beams into arbitrary direction. And to do so, we have to initially run the optimization algorithm. So let's say we want one beam at the carrier frequency and one beam at the carrier frequency minus omega. And we want the carrier frequency minus omega to be larger efficiency than the carrier frequency beam. Then what we do is we set that as an objective function and run the optimized algorithm um, and run it until it converges to the objective function. Then here, let's say we obtain objective function, then we extract the time varying voltage modulation that we obtain, and then we apply it to first meta pair, and then we phase shift it to meta and phase shift it to meta 2, and so on. Then we can again concurrently steer. Here we have been discussing mostly on transmissive mode, but if we also, as I said, we also want this to be in reflective mode as well. And this can be done by making this time varying voltages of magnetic side and electric side overlapping by phi. Then what happens is that this would flip backward. So this way we can cover 360 degrees of beam angle. And lastly, the last challenge is how to scale our metasurface to millimeter wave frequency. To do so, we need to modify the LC value in such a way that the resonant frequency matches the targeting frequency. And as I mentioned before, the inductor and capacitor constitutes the meta atom, where the inductance depends on the area of the ring and capacitor depends on the width and the gap of the ring. More specifically, the LC value is proportional to the area of the ring and the width of the ring, and inversely proportional to the gap of the ring. So now the goal is to increase the resonant frequency to 24 gigahertz by minimizing the LC value or adjusting the LC value. And we can do this by, as I said, two methods. Generally, the convention is that the area of the ring affects the resonant frequency the most. So this is why the conventional meta atom is sized wavelength of the targeting frequency over 10. But however, a millimeter wave, a meta atom with wavelength over 10 size is too small, such that once we load the smallest available varactor, its packaging completely distorts the Taylor electromagnetic surface properties. So what we do is we change the design such that we reduce the area by making it circular, and we optimize the other parameters such as gap length and radius and width. Finally, this where I want to talk about the results. So this is a single beam result. As we see, we get about 90% of efficiency for a single beam result. And comparing it to 20 dB loss for the blockage, this is very good performance once we deploy the smart surface on the wall. And also we are able to steer it to the angle that we want. Here we showed 0 angle, 30 degrees angle, and 90 degrees angle. And secondly, we tried double beam, where we have about 75% efficiency. And similarly, we got the good angular accuracy. And here we showed the double reflective beam with the 70% efficiency. And lastly, this is the result on steering accuracy. We specifically measured here on the angle of the peak of the beam. And every scenario, the beam steering angle is highly accurate. There are some noise at the end below the pi/4 and above pi/4 because the angle gets larger, the beam may not look symmetric. So this was that problem. And finally, the conclusion is that we showed the first step towards programming the millimeter wave radio environment by metamaterial surfaces. And in future work, we will soon fabricate this design to build a real smart surface prototype and focus on refining system architecture. And any questions?